So welcome back. Today we're going to continue talking about how to solve integrals. And this video is special. It involves three things that everyone loves. The natural log function will make an appearance, as well as polynomial long division and trig functions. So, sit back, relax. We're in for quite a treat today. So here's an integral. Up to this point, we might have a trouble solving. It doesn't need to use substitution yet, because if we look at this integral, all we really need to do is we just need to break it up a little bit, okay? So let's break this thing up into pieces here. So this becomes the integral of x squared over x plus 1 over x dx, which simplifies down to the integral of x plus 1 over x dx. Nothing too bad going on here so far. This first thing, the antiderivative of x, is x squared over 2, and the antiderivative of 1 over x is going to ask you to think back, I don't know, a few days or so, and remember the fact that the antiderivative of 1 over x will be the natural log of the absolute value of x plus c. So we just want to remember this here, that we have a log theorem for integration. So the log theorem from integration once again comes about from the log theorem for differentiation. That is, before we saw that if you started with the natural log of the absolute value of x and you took the derivative, you got 1 over x. Same thing here. Now integration, we can reverse this process and get a log theorem out of it. And while it was useful for the previous problem, it's really going to be useful for the next few problems. So just to reiterate, the log theorem for integration says that if you look at an integral and it looks like 1 over x dx, the antiderivative is the natural log of the absolute value of x plus c. If it looks like 1 over u du, the antiderivative is the natural log of the absolute value of u plus c. So let's look at an example. So fair warning, we're about to see a math joke, so just be prepared. So most people, when they see the integral 1 over cabin d cabin, what they think to themselves is they think, oh, well, this is just a natural log cabin, but not quite, because what they forgot to do is they forgot to add on the c. So actually, the integral of 1 over cabin d cabin is a houseboat, because it's a natural log cabin plus the c. Okay, I promise no more jokes for the rest of the semester. I actually don't think I can keep that promise, I'm sorry, but no more. I won't repeat this joke, at least for the rest of the semester. Okay, so here's a real problem that we can actually have help with using this log theorem for integration. So the first thing to recognize in this form is we can't actually break this one up. It doesn't have anything to break up. So instead what we need to do is we do need to make a substitution. So in this case, we want to look around for something to substitute, and well, there's nothing really in parentheses. So we're going to need to choose u to be x squared plus 1. So we want to add to our bag of techniques here that when we do substitution, u could be something in parentheses, it's an inner function in a composition, it can be the denominator sometimes. Basically what you do is you just try stuff until it works. So in this case, when we take the derivative, du is going to equal 2x dx, which tells me that I can replace dx with a du divided by 2x. So I will make that substitution now. So this will be equal to still the integral. For now we'll keep the x, we'll replace the x squared plus 1 with u, and we'll replace the dx with du over 2x. So that what this integral now becomes, when we simplify things down, is the integral of just 1 over 2u du, which is the integral of 1/2 the integral of 1 over u du. And this now fits our nice log theorem for integration form. So this says that this is going to be the integral 1/2 times the natural log of the absolute value of u plus c. And finally, we need to replace with our x's, so we get 1/2 the natural log of x squared plus 1 plus c after all our replacements are done. So just to review, the new idea here is to choose u to be the denominator sometimes, because that way we get substitutions that will fit into our log form. So let's look at another example of a function here. and let's try to look through how to integrate this. As always, take a chance, pause the video, and see if you can think what we should do here. So what you might be thinking, and it's a good thought to have, maybe we'll let u equal x squared plus 1, just like before, it's the denominator. It's as good as any choice. And this tells me that du again is going to be 2x dx, which means when I solve I get dx is equal to du divided by 2x. Well, let's try to substitute this in, and we're going to get the integral. Now our denominator becomes u. We still have this x squared plus x plus 1 lying around, and we're going to multiply by du over 2x. So this isn't looking good because I'm not going to be able to cancel this x off with up here. I guess I could look at this a little more and think what's going to happen. Well, it just looks kind of messy. So what we want to do first, actually, when we're faced with something like this, is we want to bring back our old friend, polynomial long division. And polynomial long division says, sorry, sometimes you need to use polynomial long division first. Okay, so let's clear this off and make some room. So in order to start computing this integral, first what I want to do is I want to simplify the inside. And in order to simplify my integrand, I have to do polynomial long division. So I need to take x squared plus 1 and divide it into x squared plus x plus 1. So the first thing I do is I think about, well, how many times should I multiply by x squared over here? And the answer, in this case, is really easy. I've only got one of them. So now I take my 1 and I multiply it by my x squared plus 1, and I get x squared plus 1, which I then subtract off because I've got one of them. And this leaves me just with an x. And this x, well, I'm not going to be able to multiply anything nice, anything like x or a number by x to get x squared plus 1, so this leaves me with my remainder. So this tells me overall when I divide I get 1 plus my remainder x over x squared plus 1. Now if you need a more in-depth review of polynomial long division, I suggest Googling it. I think when I looked at the first two examples on Google, gave videos that were really useful and really helpful. But overall what this tells us is that I can rewrite this integral instead as equal to 1, which is really easy to integrate, plus x over x squared plus 1 dx, which isn't so bad because this first integral is just x plus, well, what's the integral of x over x squared plus 1? Well, we just did this one previously. It's 1/2 the natural log of the absolute value of x squared plus 1 plus the c. So really this polynomial long division really helps us sometimes transform things. So the two big things to remember here are that sometimes you need to break up your integrals, and sometimes you need to pull out polynomial long division. Both really fun. So let's look at one more example before we move on to everyone's favorite trig functions. So here we have a nice looking integral, 1 over t times natural log of t dt. So take a second and try to guess what we should let u equal. Well, we could try to let it equal the whole denominator, so let's give it a shot. U is equal to t times the natural log of t. The issue is that when I take the derivative of this, I'm going to have to use the product rule. Usually we want to avoid the product rule. You usually want to choose u to be something simple, okay? So let's try something simpler here. We could choose u equals t, but again, if we think through it, that's probably going to be really too simple. All that's going to do is change my letters from u to t. So that's out as well. So about the only thing we have left to choose is the natural log of t. It's all that's left. So we may as well go for it. We've got nothing else to try. So this means then that du will be 1 over t dt, which tells me, well, that's actually pretty nice. Let's just leave it there. Let's not solve. Because what I can do is I can rewrite my integral now as 1 times 1 over the natural log of t times 1 over t dt. And that is great. because that's exactly what we can replace with du. So this means I can now rewrite my integral as the integral of 1 over u times du, which is something I know how to integrate because the antiderivative is the natural log of the absolute value of u plus c. Now I just got to replace my u's with my original function and I'm done. So this becomes the natural log of the absolute value of the natural log of t plus c. Pretty neat. Natural log of the natural log. Not too bad. So now we get to play with some trig functions. So the last thing that the natural log and integration does for us is it allows us to find integrals for trig functions. So we've seen the sine and cosine formulas a lot so far. So let's look at this next one, tangent. Now we remember that tangent gave us some troubles also when we tried to compute its derivative, because tangent is really sine of x divided by cosine of x. And so when we had to compute the derivative, we had to use the quotient rule. But now we're using integrals, and the integrals don't really have a good quotient rule. But they do have u substitution. So in this case, what I can do is I can let u equal my denominator, that is cosine of x, so that du is equal to sine of x, with a negative out there, of course, because I don't forget the negatives, dx. And now I can do my replacement. What I'm going to do is I'm going to solve for dx so that dx is equal to du divided by negative sine of x. And now I can substitute in my integral. I can keep the sine of x there for now. I can replace the cosine that's in my denominator with u. And I can replace dx with du divided by negative sine of x. And now I can see what happens. These signs will cancel. And so what I end up with in integral is the integral of negative 1 over u du. And so the antiderivative of this is the negative of the natural log of the absolute value of u plus c. And the final step, replace u's in terms of my original function. So I get the negative natural log of the cosine of x plus c. Now, fair warning for all of these. Anytime you use trig functions, your answers might not meet the back of the books. They might not match up exactly because trig functions have identities. Same with natural logs. There's lots of things that can happen with both of these. Therefore, it might take some work to see if your answer is the same as the back of the book. Let's do another example because you can never have enough practice with u substitution. So in this case, take a moment again to try and think, what do you think your u should be? So in this case, I'm going to choose my u to be w squared. W squared fits the bill. It's inside parentheses, it's in a composition of functions, it's looking good. So this means du is going to be 2w dw. I like to see that because that's right there, part of my integral. So this means I can replace my integral here that looks kind of complicated with a somewhat nicer looking cosecant of u times du. And this is an integral that I can solve. It's right up here in the table. It's the last one. So this says that this integral is going to equal negative natural log absolute value of cosecant of u plus cotangent of u plus c. And so I might be tempted to think I'm done, but I need to replace all my u's back in terms of w. So as a last step, this becomes the negative natural log of the cosecant of w squared plus the cotangent of w squared, finish the absolute value, keep that c on the end. So with all of these, the basic idea is either to get it to fit into a pattern that you already know, or to get it at least close to a pattern that you can integrate. So that's overall the goal with substitution, getting it towards a pattern that isn't as complicated, that is one that you know. As always, try the quiz online. Then you should have a handout that has some for you to practice for class tomorrow, and post a question on Blackboard. Oh, and take the quiz. Have a good day.